In digital electronics, there are two more states apart from 1 and 0. These are X and Z, which you know already. To accommodate these states, we have altogether 3 different case statements in Verilog. In today's episode, we will cover all of them through examples. So, stay tuned till the end of this video. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. First, we'll do an introduction to the case statement in a very generic manner. Next, we will talk about the case structure itself, and we will see how we can use a single, multiple commands and combination of the two in writing an entire list of case statements for various case values inside a single case block. Next, we will go through 5 different examples using the case statements. And as you know, as a student, when you are learning the language, the structure is okay. But however, if you do not go through the examples, it is very, very difficult for you to write a code by yourself. Next, we will emphasize on the points that should be noted while dealing with a particular case statement in Verilog. Next, we will talk about how to detect the X and Z using a regular case statement. And remember, this is a very good question for any interview in Verilog because we also have case X and case Z in Verilog. However, we can use a general case statement to detect X and Z. So in this point, we are going to talk about that only. Next, we will talk about the case Z and case X examples. Next, we will talk about the CaseX and CaseZ with examples. These are advanced case statements in Verilog, and you will see this is a basic fundamental difference from any programming language, because in any other programming language you will find case or switch case, but you will not find this kind of specific case Z or case X. These are very much specific to Verilog, so you must have a good knowledge about them and using them. That's why we are giving examples so that you can understand it and write the code with case Z and case X. Next, we talk about the constant expression in case. So in the case statement, we generally use an expression. However, we can use constants. Constant is something that is constant over the time and it don't have any expression. So it's a constant. So that we can use in case. And please remember, this is a very important question for the interview. Finally, we will summarize our entire discussion in the final slide. So this is the menu for today. So without any further delay, let's begin. Introduction. The case statement is a multi-way decision statement. Multi-way means there are multiple cases for which the digital control can go to different expression or values. So this is the multi-way. Or rather, you can say it's a lookup table. So case 1, value 1, case 2, value 2, case 3, value 3. So this way, it can have a lookup table. So this is a decision statement and it's a multi-way. It tests whether a digital expression matches among a list of predefined other expression or branches. As I have said, it have a predefined list starting from 1, 2 and up to n. So among those lists, it will search for the matching case, and we also have a default statement. If it doesn't match with any one of the expression here, it will go to the default at the last. I will show you. The case statement allows a multi-path branch based on comparing the expression with a list of case choices. It's very easy to understand and we will exemplify it so that you better understand it. Case choices may be simple constant or expression or a comma separated list of the same. So when you are writing case within parentheses, what can come? A constant can come, a expression can come, and a comma separated list can come. These 3. Definitely we will go through the example. There you will see this. Upon exhaustion or exclusion of the list, control enters into the default block. That means when all the cases from the lookup table are finished, it finally enters into the last block, that is the default one. That means the checking counter has not matched with the values or the expressions, those have been specified before the default one. And once it enters the default block, it executes the default action specified using the default statement. It is a good practice to make habit of putting a default whether you need it or not. So this is very, very important because in Verilog, you might have to debug your code based on different case scenarios. And in some particular case scenario, say your expression is not matching with the values that you have defined through the case. So it will enter into the default case and you will find, okay, all these have not been matched. In case you need to insert some more case or you have to modify some of the existing cases, that call you can take at that time. But remember, the default block will help you to go there. Otherwise, if you do not specify the default block, then you will be in a wild goose chase. So you will not understand what is happening. If the defaults are don't cares, define them as X. As we know that in digital we have X, right? So if it is don't care, define them as X. Case excels when many tests are performed on the same expression. So if the same expression is there and the case operates on the same expression but however for different values to the lookup table that we define inside the case. Case works well with which digital circuit? Muxes, decoder and next state logic. And the next state logic is also termed as the FSM in digital design. In some later episode we'll cover muxes and decoders, you already know. So those things go well with the case statement. So we're done with the introduction part here and with this slide. So let's move on to the next slide. Case structure, single statement. So here we will give a structural example. It's not a code example, it's a structural example of the case with using the single statement in each value. So here case variable or concatenated variable, or we can have a comma separated values also. So it start and here the lookup table starts here. For value 1 we use colon as a separator and on the right hand side there will be single action statement. Here it is a comment. However, in your case this will be actual Verilog statement. Next we have value 2, for that we have action statement 2. Value 3 we have single action statement 3. So this is single statement, that means one statement, not more than one statement is here. And this way we continue and we reach value n and action statement n. And finally we have the default statement and we have the default action statement. Generally this is a print command like $display or something where you actually give a echo on your screen so that you know that all the things are not matched and your control has entered into the default one. So this way you actually do the debug. This is the structure and we end our case with the end case keyword. And this is the basic structural example, not the coding example. The structural example using single action statement. So you have one particular statement for a particular value and this way you build up the lookup table. Case structure with multiple statements. In last slide we have talked about the single statement. Now your question is, okay, how we will be writing about the multiple statements in the case structure. So this is the whole kind of case where we will be going through the structural example, not the code example. Here we have the case and we have the variable or the concatenated variable, or we can have a comma separated values also. Here we have the value 1 and then since we are containing multiple statements, we start with the begin keyword. This is for value 1. This is not of the case. This is for this begin is for value 1. Now we have multiple action statements and then we conclude it with the end. This begin and this end belongs to this value 1. And here we have multiple action, although I have written one single particular comment, but however you can push multiple statements inside this begin and end for value 1. Next we have value 2 and we again have begin. And we have multiple action statement and we have the end to end it. This begin and end for value 2. This way continue and we reach to the value n. And here we again have begin, we have multiple action statements and then we close it with the end. So and this end is for value n. And next we reach at the default statement. Here we can have also multiple statement and we have the begin here. And we have the multiple statements and we have the end. This end is for default one. And to end the case, then we write the end case. So this end case is for the case statement. This way you can write multiple action statements for the case structure. So this is a structural example. It's not a code example. It's a structural example. You understand better how to write the case statement as a beginner. Now we are done with this slide. The next question comes that, okay, now we know that we can write single statement and we write multiple statement. In actual case, it may happen that both are combined. How we write that? So in next slide, we are going to talk about that. We are discussing here about the combined one for the two things, that is the single and the multiple that we have just seen in last two slides. So here we start with our case statement and we have variable, concatenated variable, and we can have a comma separated values. Next, we have value 1 and we have single action statement 1. We have value 2 and begin. You can see begin means we are having multiple statements. So here I explicitly write single action statement to A, to B, to C. So these are 3 different single statement contained within value 2, and we end this block with end, and it is for value 2. Next, we have value 3, which have action statement as a single action statement here, and we continue further. We reach up to value n, and where we have action statement n, and we have the default one, and we have default action state. We end the case with the end case keyword, and we are done with the structural example here. And the point is here, this particular structure can be anywhere, there, here, anywhere, or multiple, means don't have to be in one place, it can be in multiple places. So this is a structural example. Now we are done with this particular slide, so let's move on to the next slide. We have case example 1. So here we will go through the code example. So far we have seen the structural example, means how the structure can be altered and all, and they can be combined. Now we have the case example. So these are realistic example. However, we are not writing the entire code with the test bench, just for the case block, so that you get efficient in writing the case statement. First, we have the range A, which is 15 down to 0. We have result, which is a range, and it is 9 down to 0. So both are buses. And then we start our case, and we have range A as the case expression, and the values which can be possible for range A is 16 tick D0, and the action statement here is the result will be this one. So result and range both are buses, so this way we are writing the values of the buses, and here we have 16 tick D1 and we have the values. So this way we continue the lookup table till we exhaust all the values, and in the default block we have written here result equal to pick bx. This is some x condition we are putting. You can also give here a $display command for your debug purpose, right? And we end our case example with end case. You can see that here we have used the single action statement format for the case, and here we have dealt with 2 buses, range A and result, as for the conditional value of the range A and the result as an outcome. However, you can see these are the width of the buses are not same, so you can understand that this is a very actual example where the buses will be different, they will not be same. However, you are using them inside the case statement. So this is a very good realistic example of the case using single action statement. So we are done with this example. Let's move on to the next slide. Here we will have 2 examples in a single slide. So let us start with the first one. Case ALU counter. You can see this is an expression ALU counter, and here we have 2 tick B00, and then what will be the action, that is ALU out will be A plus B, and similarly if it is 2 tick B01, ALU out will be A minus B, 2 tick B10, ALU out will be A and B, and default is ALU out is 1 tick BX. And these are treated as don't cares for minimum logic generation. We have done with the case example here, and here we end case. Here you can see that it is not a constant here, rather than this is an expression, which is a difference from the previous example here. So we are done with this. Let's see the next example. We are staying in the same slide, so let's start here. We have case X, Y or Z. So this is a kind of comma separated values, which means that this case happens if X or Y or Z, right, any one of them is 2 tick B00. So here if 2 tick B00, ALU out is A plus. That means case if X or Y or Z is 2 tick B00, this expression must be executed. Similarly, 2 tick B01, it will be A minus B, and for 2 tick B10, it will be A and B. And for default statement, we have ALU out equal to A pipe B, and we end the case with the end case statement. This is another kind of example where we have exemplified, which is the main thing here. This is a comma separated values, and this or this or this can have the value this. So this is a different type of case example that you have just came across. So previously there was only one single. So later we will have some example with the concatenated one also. So we are done with this particular slide. So let's move on to the next slide. Case example 4. Here we have a single example, but I have broken the code into 2 parts for the sake of the space in this particular slide. We start our code here, and we have a module D2X8, and we have select and out. This is a priority encoder, and we have input 0 to select, output 0 to 7 out, and this is out is a range. You can see these and these are buses, and this out is type range. And here we start our always block, and the sensitive variable is select, that means this one. And here we begin our code, and here we write out equal to 0, and we continue our next part of the code here. And here we have the case, and here we have the select. Again, here the expression is select. So select is staying here in always. So whenever the select changes, this goes from here to here in the case. So the sensitivity is tied up with select, and that goes to the case directly. And here we have our first lookup table statement that select if it is 0, then out is a bus, right? So the 0th bit will be 1. Next, for 1th bit will be 1. And this way we continue further and we reach up to the default one. Here the default one is display, nothing is set for default. So this is acting as some debug command. So this notifies that none of these has happened and nothing is set for the default. That means the above ones have not executed. And we end our case with the end case statement. Now we put a end. Now this end belongs to always, right? And finally we have a end module, and this one belongs to the module statement. So here our code is completed. You have grasped the meaning, how we can use the case, and this is another type of example. And we have used the debug statement here with the $display, and we are done with this example. So let's move on to the next example. So here let us start our example, and here we start. It is a 4-to-1 multiplexer, and we have module, and we named it as a case 1, and we are writing input 7 down to 0, A in, B in, C in, and D in. So 4 inputs, input 1 down to 0 select, and output is name is 7 down to 0 D out. So these are the input and outputs of this module. And here we have always block with the sensitive variable is select, so this one. And here we begin our always, and here we start our case, and you can see once the sensitivity comes to always, it get transferred to the case, and there it is checked for the values that we are listing here. The values, if the select is 2 tick B00, this expression will execute. The D out will be A in. For 01, D out will be B in. For 10, D out will be C in. And for 11, D out will be D in. And here we end our case. So you can see our case has ended with end case, and we end it. So this end belongs to the always, and we end our module here. This belongs to the module. So entire code is completed here. So this is another example which I think you can grasp the meaning how to write the case statement. And let's move on to the next slide. Case points to be noted. So here we are talking about different points that we should note properly while we are coding for the case statement in Verilog. Now here it goes, starts. In the case statement expression comparison, the comparison only succeeds when each bit matches exactly with respect to the values of 0, 1, x and z. So these 4 values does exist in digital, and the case expression has to be evaluated, either each of them or the combination of them. This is our thing we should remember. So that means 0, 1, x and z can come in a realistic scenario. Next, as a consequence, care is needed in specifying expressions in the case statement. So when you are using the statement, right, you must be very careful. The bit length of all the expressions shall be equal so that exact bitwise matching can be performed. So you must be very careful about the bit length. That is, when we have an expression, we have a variable, the bit length, that is the LSB to the MSB, how many bits are there. So that thing is very important there, and matching, it should be matching throughout the code. Next, the length of all the case item expression as well as the case expression in the parenthesis shall be made equal in length of the longest case expression and case item expression. You have to be very careful about the length. That is what we are focusing here. So whatever in the case, that should be the superset of all the expression for the same thing. If you have some other versions, that should be there and it should be the superset. If any of these expression is unsigned, all of them shall be treated as unsigned. If any of the expression are signed, then all of them should be treated as signed. So you have to be very careful. Again, apart from the width, you must be very careful whether it is unsigned or signed. So you have to stay in the same convention. That means either you stay in the signed one or the unsigned one, whatever is applicable there. It's not your choice, whatever is applicable there. You are done here with the points that you should note while you are writing a case statement in Verilog. These things do not exist there in other programming languages. These cautionary points, these things you have to remember only in Verilog. That means in the hardware description language. So we are done with this particular slide. Let's move on to the next slide. Case detecting X and Z. So as I have mentioned in the menu, right there, I have mentioned that this particular slide will be very important for your interview purpose. You can be asked that we have already case X and case Z is there. So how you can detect the X and Z using a regular case statement? You focus on this slide with great importance, and let us begin here. So here we'll give example code here. Our case starts with case and we have a variable sig, that means signal, and signal is 1 tick bz, display signal is floating. If it matches with 1 tick bx, display signal is unknown. And we have default that the signal is, we print it explicitly. So this way the case can detect the Z and X. Now this is 1 bit, right? If it is more than 1 bit, then you can have more than 1 bits here itself. Let me clear the markings. If this is more than 1 bit, it has some width. So here you can modify accordingly. Here we have the end case, and this ends the case statement. It's a simple, yet it is very important for the interview. So you are done with this example. So let's move on to the next slide. Advanced statements, that is case Z and case X. In a case expression, each bit matches exactly with respect to the values 0, 1, X and Z. So this you are very much familiar. I have re-emphasized it here because we are talking about now the case Z and case X special case statements that exist only in Verilog. You have not seen, or you will not see such kind of special cases or switch case in programming language. It is existing only in the hardware description language. Next, two other type of case statements are provided to allow handling of do not care condition in the case comparison. So you know Z and X does exist, you cannot ignore them. So to include them and handle them properly, we have special cases, that is case Z and case X in Verilog. One of these treats high impedance value Z as do not care, that means this is case Z, and other treats the high impedance and unknown, that means Z and X, as do not care, that means this is for the case X. Next, these case statements can be used in the same way as the usual case statement. That means the writing fashion is same, but they begin with keywords case Z and case X. So these are reserved keywords in the Verilog library. So you have to use these judiciously where you have such cases inside your Verilog design. Do not care values, Z values for case Z and X values for case X in any bit in either of the case expression or the case item shall be treated as do not care condition. Basically, the Z and X, either Z or X or Z and X combined, are treated as don't care conditions in the expression, and that bit position shall not be considered. If particular bit position is assigned for Z or X or Z or X or Z and X, that should be treated in a very judicious way. So we are done with this particular slide. So let's move on to the next slide. We continue our discussion here for the case Z and case X description and definitions. The do not care conditions in the case expression can be used to control dynamically which bits should be compared at any time. So this is another thing, the dynamicity, that is another very important factor of this, because in the lookup table in the regular case statement, the left hand value from the colon right here, it should be something which is fixed. It's not dynamic. However, here in the case Z or case X, you will see the examples, how they can be dynamic, how we can write them as a dynamic. You will see this is a stark difference with the regular case statement. The syntax of literal numbers allows the use of question mark. That means this question mark in the place of Z in the case statements. This provides a convenient format for specification of do not care bits. To denote the do not care bits, we use a question mark for Z cases. Case Z, specifically we are now summarizing for case X and case Z. So start with case Z here, treats Z as the don't care in the expression, and the position that can contain Z are represented by a question mark instead of a fixed bit. In regular case statement, we use either 1 or 0 as a constant number there. Instead, for Z, we can use a question mark, and this gives a dynamicity. Here we have talked about the dynamicity, right? And this particular expression gives the dynamicity of that expression. You will see when we give the example. CaseX treat both X and Z as don't cares together. Now this is a superset of CaseZ. However, Verilog has a provision to use either Z or CaseX. Both you can use or either one you can use. It depends on case by case basis. That means not the case of the Verilog, but the real case where you are coding. And for this, the case X, the position that can contain Z or X are represented by question mark or X. In the example, you will see that here these are used to denote the do not care. That means the don't care position. That means it gives the dynamicity of the case X and case Z. So for case Z it has the question mark, and for case X it has the question mark or X. We are done with this, all the definitions and theoretical discussions here. Let's move on to the next slide. CaseZ example. We have a bus here, IR, which is 7 down to 0. And we have case Z, this is for CaseZ example, IR. And here we have a left hand expression, and here you can see here the marking. All these bits are dynamic to be Z, and it could be any expression. This is fixed and these are dynamic. So this can be Z, anyone can be Z, anyone can be else. In that case, the instruction 1 should happen. That means that should execute. In the similar fashion, we have this expression, this and this. So here you can see here 1 bit is constant, here 2 bits are constant, here 5 bits are constant. Here we have 6, I think 3, 3, 6. Yes, 6. And here 2 are dynamic, here 3 are dynamic, here these ones are dynamic, and here most of the things are dynamic as to give place for Z. And we end the case with end case. Now let us give some explanation of this. So the above example of the case Z statement, as we have just talked, right? It demonstrates the instruction decode whether the values of the most significant bit select which task should be called. So here these are tasks or instruction set, what should be there. And the most significant bit IR is A is 1. Then the task instruction 1 is called regardless the value of the other bits in IR. So this is very clear from these state of values and corresponding actions. That means this lookup table. So we are done here with the case Z example. Let's move on to case X example. Here we are in the slide of the case X example. Here we start our code with the reg, and this is 7 down to 0 R, and there is a mask. And we define a mask as this one, and we have case R XOR mask. So this is an expression R XOR mask, and we have this kind of lookup table here. So here. So you can see here these bits are constant and these bits are constant. And these 2 bits, right? These 2 bits are don't cares, and they are specified with X because here we are dealing with case X. We end the case with the end case statement, and you can see how we can write a don't care condition in the case X. So you have seen the case Z example and you have seen the case X example. Now let me give the text description. So here this is an example of case X, and it demonstrates the extreme case of how do not care conditions can be dynamically controlled during the simulation. So these are dynamic. So that means this one, both can be X, or one could be X, someone could be other things. So this way, this becomes very dynamic. So this is not a constant expression. This is a dynamic expression. This dynamicity is given by the case X. And this dynamicity, one thing I would like to mention, actually reduces the number of cases that we are writing as a lookup table. Next, in this case, if R is equal to this, then the task stat2 is, this is a typical example, right? You understand this particular case example or using the case X statement. So here we are done with the slide. Let's move on to the next slide. Constant expression in case. Before beginning, I would like to talk here that this is a very good slide that question can come in the interview. That means we know that in case we use the expression, and tell me or show me an example where we can use a constant in the case. So here we start with range 2 down to 0 encode, and here we have case 1 and we have encode 2 display select line 2, and we have encode 1 and display select line 2. And for encode 0, we have select line 0, and default here we have missed out the colon and it has the error message. Now let me explain how this constant is working. A constant expression can be used for the case expression. The value of the constant expression shall be compared against the case item expression. That means this value is compared with this value, right? So encode can have multiple values. However, this one has to be compared with each bit. So this is a single bit, this is a single bit and this is a single bit. This way the constant expression is compared with here. Similar way we can have a constant value and we can have a concatenated value here also, that we can also have. In this example, the case expression has a constant expression 1. The case items expression, that means bit selects, are compared against the constant expression of a match. So here these bit selects are compared with the constant expression. So here we are done with the constant expression, and as I have given you a tip that you can use a concatenated version here also. Here you can have a concatenated version also. However, this will change somehow according to that. Those can be asked in an interview. So here we are done with the constant expression in case. Let's move on to the next slide. Summary. The case expression given in the parenthesis shall be evaluated exactly once and before any of the case item expressions. So whatever inside the parenthesis is there, that should be evaluated first, and then that should be compared with all the values mentioned in the lookup table below. Next, the case item expressions shall be evaluated and compared in exact order. So this is another good point to be emphasized, which they are given, because in digital design we sometimes have a kind of methodology of design where this order does have a significance. So in that case you have to focus on the exact order. During the linear search, if one of the case item expression matches the case expression given in the parenthesis, then the statement associated with that case shall be executed and the linear search should terminate. So this is the most important point. Once you have a match, it goes out of the case statement. By executing the lookup table expression, it goes out of the case expression. It do not search any further. If all the comparison fail, that means all the lookup table that we have written, they are failed, the default item is given. Hence, I am emphasizing this point again and again in this particular episode, that the default one is good for your debugging purpose. That means you have written the case conditions correctly, or you have not missed out, or in case you have missed out, you will have the default one to notify you that you have missed out. Somehow you have to go back and check, debug by yourself, which particular case I have missed out. Default is given, the default item statement shall be executed, and this is a good opportunity of the debug. The case statement differs from the multi-way if-else-if construct in two different ways. First one is the conditional expressions in if-else-if construct, that means the nested one, are more general than the comparing expression with several others, as in the case statement. So case statement, you have a specific lookup table or a lookup chart, which you do not have in if-else-if construct. So it's more systematically listed in case statement, which is not there in the nested if-else-if or if-else-if construct. The case statement provides a definitive results when there are x and z values in the expression. So this is another striking difference, because we can detect the x and z. Also, we have the case x and case z, which we do not have in the if-else-if construct. This is very important from the digital design perspective. You can be asked in the interview. So give the difference of if-else-if construct versus the case. The case, once they say, right, you can mention about the case x and case z, because they are specific to Verilog. So you don't have to go for the case. You can answer this. We are done here with the summary slide, and let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.